Remember, we introduced the surface integral and we discussed the integration of a surface integral on a scalar function, if you like. Okay, so if the scalar function, just recall that one for you to to remember it, and then continue. Okay, so this is it, because the part that you use in science is surface integral of the vector fields most of the time, and you have three great theorems in in this part, and in physics it's going to be used in the concept of as I talked about it the other day, in the concept of the fluid flow, and in the case of the electrical fields. You have a couple of theorems really. If you do advanced physics, they are all calculus, and they express it exactly the way we are going to do it today. But instead of the f, which is the the function, the vector field for us, they use the actual one. So for the first time, they are all discovered in physics. Okay, then we are going to bring it up over here. Okay, so vector field of the surface integral of the vector fields. Okay, so if you have a scalar function, okay, so recall that it's good to have a good idea of what we did and then what we are going to do. So recall that it's the one that we know so far. Recall that if the surface S, okay, is given, and F is going to be a scalar valued, real valued, a scalar valued or real valued function. Okay, real valued function on on S. Okay, with the usual, with continuous partial derivatives, with continuous partial derivatives, then the surface integral, then the surface integral, and the surface integral of f along on S, if you like, is given by, that's the formula. So this is going to be a kind of a double integral. That's a surface A's. So the function is f of x, y, z is a scalar valued function, and it's going to be differential of the surface. Differential of the surface, this would be changing to the, a double integral on the domain D. Okay, on the domain of the D, and then your f is going to be, and this is it. This is going to be f of x, y, f of x, y, and f of x, y, g of x, y, then the square root of 1 plus g of x squared plus g of y squared, then the dx dy. Okay, if the parametric equation of S is is going to be in the form of is something like z equal to the g of x comma y. You know that this is going to be the surface of this function, and in general, if this is going to be the surface integral f x y z ds s, this is going to be a double integral. If the surface is given to you by a parametric equation, this is a parametric equation, but we get the variables, the parameters are x and the y. But in general, if it's going to be anything else, then you evaluate the function at those parametric form. Okay, this is going to be the one. If you do this one, you have to multiply by the normal vector, which is the same thing here. Okay, the norm of the UV, and then this is going to be du dv. And this is going to be the case where S is given by, okay, given by this equation, R of U and V is going to be your parametric equation. Okay, most of the time it's going to be, the scalar one, Z is Z of XY. So just use this formula. That would be easy for you. Just do it quickly. If it's going to be giving you a parametric equation, just use the parametric form. And we did it, and we gave you 2 examples the other day. And there are a couple of nice ones we are going to get from your review. Okay, so this is the case for the scalar valued function. So what we're going to do, we are going to replace this function by a vector field. When you change it to the vector field, then this is going to be a vector, so you cannot have this type of product. So what you do is you change this product into the dot product. So it's going to be f dot the differential of the, okay, differential of the surface. Okay, then your formula here is going to be a kind of unchanged, this format. Then remember the way we did it before. So we are going to replace this one by this is going to be f of rv dot, okay, dot the normal vector du dv. And so the change, I just wanted to see it, compare them together. So now if, and so now the general form is going to be the following. If we have a vector field, fx, y, z, you know that the vector field in general, pi, qi, qj, and rk is going to be a vector field. A vector field can be electrical field or can be, okay, it can be this one going to be, can be fluid, okay, fluid force, fluid flow, we call it fluid flow. Suppose this is going to be, this is going to be the kind of this is going to be the temperature, body temperature. If you're going to be body temperature, so this would be heat fluid, okay, heat flow, we call it, okay. And then by the vector field, you are going to have rate of change of that force, whatever it is. So if this is going to be a vector field, okay, a vector field, and S is going to be, okay, vector field, and S is going to be a given surface, with a parametric equation, then the parametric equation is, as usual, it's going to be R of UV. The usual practice of the, remember, it's going to be X of UV, Y of UV, Z of UV. If this is going to be the case, then the surface integral, or just temperature, okay, along the body, if you like. Then the surface integral of F, heat, I mean by temperature, of F across, okay, across the surface S is going to be defined by, okay, it's going to be defined by, this is it, it's going to be a double integral on the surface F, but it's going to be F dot this time, ds, because it's the vector form, if you like. So this is going to be again the domain that you find for the double integral. Then it's the same thing, f of r of uv, evaluate the function on the surface integral as we did it for the top, but this time it's going to be dot and uv. That's a normal vector that we're going to find. So vector, you multiply them together, that makes sense, and make it the number. Then when you get the number, then you have to differentiate it respect to the u and the respect to the v. Okay, so it's not going to be a scalar function. Or in short, sometimes they write it down in this form, the double integral, okay, s f, let me write down here. So it's a double integral on s f dot ds. Dot ds is going to be the same as f dot n, if you like, the normal vector, dot n ds. So this means if you are going to be interested to find out the rate of, okay, the rate of change or the speed, the rate of change of the heat flow through a body, through the objects. So the way you're going to do it, it's going to be the same as the amount that you're going to consider as this. It's a kind of normal component of that field, which is going to be f dot n over here. Okay, and this procedure was first used in physics. Okay, it was done by Gauss for the first time. The expression that they have over there for this type of quantity, they refer to it as a flux. Okay, so you have to know this one. So this quantity, okay, so this double integral or quantity sf dot, it's a number, that n ds, this quantity, they refer to it as, in physics, they call it the flux. It depends on what type of source F they have. Okay, most of the time it's going to be heat flow, or that's it, fluid flow. It's called the flux of vector field. Sometimes in some problems they simply ask for the flux of the vector field. You must know it. Flux of a vector field F, okay, through F through the surface of S. Okay, there are quite a lot they do in physics, you know. Sometimes the name Gauss. Okay, Gauss is the one again responsible for this. Okay, some of this expression is used, and there is something related to heat in physics. They call it the Gauss law. Okay, I'm not very much familiar, but I know the nature of those. So if you have done anything in physics, or you are going to be measuring physics or electrical engineering, etc., surely you are going to see this type of ideas over there. Okay, you see the integral, but they call it something else. Okay, so this is the vector field on the surface integral, the application of whatever we did. And so you should be able to find it for us. Okay, so we give you one and we ask you to do it. We give you a force, okay, vector field. It can be, you know, heat flow or something else, and then all the information, and patiently you have to find it for us. Okay, so you will see one of them on this final. Okay, and we try to give you something. It can be done in a short form. It's not bad. Be patient and practice to make sure you have all the formulas, everything available. Okay, so we wanted to evaluate, and that's it, the surface integral on the surface S and f dot ds. Okay, where the field is this one. You have a better one, of course, on the practice one that we're going to do it. So let's start with this. And the surface would be given to you. Okay, and S is a surface. S is going to be a surface. It's a surface with the parameterization, if you like, with the parametric equation, with the parameterization or parametric equation. That's it, R of uv equal to u squared v, and you have a u cubed minus v cubed. That's a parametric equation of your surface. And this is where u is between 0 and 1. That would be the domain that you have to integrate. And the v is between 0 and 1. And you know, the domain of these are going to be 0, 1 cross 0, 1. Because when you change it to the double integral, you integrate on the domain of this surface. The domain is going to be in two-dimensional, so you need to know what's going to be now the range of the x and the y in terms of u and the v when you integrate it. Okay, so and that's it. You have all the information and you want to find it. And that's it. Your formula is going to be, okay, remind you the formula. That's going to be the surface integral on the vector field. So it's going to be a double integral. This is going to be the surface integral. So you have to find the f of r of u v. Okay, that's one dot. Okay, dot n of u and v, and then of course the s. Sorry, the u dv, the u dv. And you know when we change it, then we come back and we take care of the form that we're going to have. If you write du dv, they have to write the domain in d. You know that you change it to double integral. So you have to prepare. Preparation is going to be, of course, the normal vector first. Okay. So this is it, the normal vector first. So n, the normal vector, is going to be what? Remember, it's going to be ru cross rv. You have to find it. So this is your r. So your r is u squared v u cubed minus v cubed. So find the partial derivative with respect to the u. With respect to the u, that give you 2u, 0. Okay, and that give you 3u squared. 3u squared, and you find the partial derivative with respect to the v, which is going to be 0, 1, negative 3v squared. Okay, go and form the cross product. So the cross product ru cross rv, remember it's ijk. So it's going to be I, then you get the j and you have a k. So this would cover 2u, 0, 3u squared. And this is going to be 0, 1, negative 3v squared. You have to find it. Okay, get this determinant. It's going to be I times. Eliminate the first row column, so that gives you 0. So this would be 0 minus 3u squared minus j. Eliminate the first row second column, so that gives you negative 6uv squared minus 0. Okay, that's a j, and the k. Eliminate the first row last, so that gives you 2u minus 0. Okay, so eventually this is going to be negative 3u squared I and a plus 6uv squared j and the 2uk. 2uk, okay. So in the component form, this is it. You get the negative u squared, 6uv squared, and the 2u. So this would be your normal, this is going to be your normal vector. Okay, this is a normal vector. Okay, any question? So what we need to find f of ru, then dot product with the n. Okay, these numbers are done. So I'm going to get the f of ru and then dot product, and eventually we integrate it. Okay, so that's it. So remember the function. The field is going to be 0, 0, x. That's a field. So evaluate it at r of u v. Okay, so you know that r of u v, these are going to be all 0. So that gives you 0, 0x, x in the parametric equation, RUV, what was the x? You see, that is RUV and the x is U squared. So that gives you U squared, evaluation of the function at that vector. Okay. So now we got the dot product. That's going to be f dot n. F dot n is going to be f is 0, 0, U squared dot n. A normal vector, we have a negative 3 U squared, 6 U V squared, and the 2U. That's it. So if you multiply them together, that's going to be 0 dot product, remember, that would be 0. And if you multiply these two together, that give you 2U cubed. 2U cubed, which is going to be 2U cubed. Okay, that's it. That's f dot n, which is going to be a scalar. Now we are ready to integrate it. So the double integral on s f dot ds is going to be a double integral. Okay, the result is 2u cubed and the du dv. And you know that u and v was between 0, 1. So that would be 0, 1, and that would be 0, 0, 1. Okay, so we get the 0, 1, 0, 1, and then integrate it. So it's going to be 0, 1, integrate over here. So that gives you 2u to the 4th, okay, over 4 from 0 to 1. Then the dv. So this simply would be 1/2. 0 to 1, 1/2 of the dv. And the result would be a half. So it's going to be 1/2 of the v from 0 to 1, which is going to be 1/2. Okay, so that's it. So the surface integral is going to be equal to the 1/2. And then you're done. Okay, so it's it's straightforward, but depends on this force, the field that we have. Is depends whether it's going to be electrical field, electrical force, okay, or it's going to be heat flow, or then you have interpretation at the end. Okay, so this is it. Any question? Now, when you're dealing with this type of integral, there is the one that is very challenging. So I give you that one, and then there is going to be a normal vector. I let you take that normal vector and bring it to the test if you like. This integral, it's happened a couple of places. If you want to integrate on a sphere, if the surface is going to be a sphere, it takes times to find that a normal vector. So I do it for you, but you can write it down as a formula and bring it in. Otherwise, it takes time quite a while. And you have a couple of problems related to that. Okay. So let's these are going to be straightforward when this vector field is going to be nice, or just the sphere is nice in the case of this parametric equation. But when it's going to be a sphere, it needs a little bit of attention. Okay, so I do this one for you. Be patient. I get the formula, then you can use it. I just wanted to say, you make a note. Normal vector for the normal vector for the sphere, if you hemisphere or the sphere. So from time to time you have this problem. It's part of the deal because it's using application. They ask you, they use this expression. Find the flex means just surface integral. You must know it. Remember work, we already talked about it for the line integral. F dot dr, or C, that was work. But over here, you have the expression of find the flex. Again, when you're dealing with this application, this makes sense. Flex of this function, f equal to x, y, 0. Okay, through, you want to do it through the upper hemisphere, the upper, okay, upper hemisphere. That's your surface, S of the sphere, A sphere is unit sphere. X squared plus Y squared plus Z squared equal to 1. Okay, it's the one. There is one in the review that you want to do it along the, okay, the paraboloid. It's a cylinder paraboloid, or we will see it. That's easier because you don't have the Z square when it's going to be paraboloid. But when you have the Z square, it takes time to find the normal vector. Okay, that's why I wanted to say it. Now, you know what does it mean? The flex means surface integral on the vector field. So you have to find the surface integral over the vector field. So this is going to be the question. And you know that this is going to be the same as the surface integral of the f dot n ds. And then you parameterize it. You go on the domain D, and this is going to be f of r of u v dot normal vector u v and the integral du dv. That's your formula. Flex, and we talked about this, that's flex. That's going to be the flex that you have to find. Okay, so it's the same thing with that difference integral. Okay, so just give me a few seconds. Okay, so there you are. What's the challenge? The challenge is, of course, finding the n. So you have to parameterize this equation, okay? So you have to give us a parametric equation of the sphere. The parametric equation of a sphere is what? Is a spherical coordinate. So you have to know it. So what we are going to do is we are going to use, okay, so that's it, using the spherical. Okay, that's it. Using the spherical coordinates. Of course, with, remember you have x squared plus y squared plus z squared equal to 1, with the rho equal to 1, the radius of the sphere. Okay, use the parametric coordinates for the parameterization, or for the, yeah, that's it. For the parametric equation, if you like, for the parametric equation of S. Okay, now what's this? Remember, it's going to be R of theta and phi. Remember, the x coordinate was a rho. Cosine theta, sine phi. Rho is 1. So it's going to be cosine theta, sine phi. That's the x. Y was what? Rho sine. Rho is 1. Sine of theta, sine phi. And the last one was what? And the last one was rho cosine of the phi, z. So it's going to be cosine of the phi. Cosine of the phi. You see, this is going to be parametric equation of this sphere. So if you need the sphere, this is going to be your equation. Now you have to find the normal vector. You know that the normal vector you have to, so your n is going to be r theta cross r phi. Okay, this is going to be the case. Now you have to differentiate, carefully differentiate. So r of theta is going to be derivative respect to the data. So that give a negative sine of the data, okay, sine of the phi. So this is going to be cosine of the data, sine of the phi. Okay, and this is going to be negative sine of the phi. Okay, that's all of data. Oh, I'm sorry. This would be 0. I missed it. We differentiate respect to the data. That's phi. Okay, go ahead, get the derivative respect to the phi. What is phi? Sine would be cosine, so that gives you cosine of the data, cosine of the phi. Okay, that would be sine of the data, cosine of the phi again, and that would be negative sine of the phi. Okay, so this is what you have. Cross multiply to get the normal vector. Okay, if you cross multiply it, n is equal to the r data r phi. Carefully put them together. So this is going to be I. So I'm going to put this one so I have enough space. It's a negative sine of the data, sine of the phi. The first component here is cosine of the data, cosine of the phi. You get the j here. The second component here is cosine of the data, sine of the phi. And this is a sine of the data, cosine of the phi. This is 0. And this is, I'm sorry, that's k. That's a k, and this is going to be 0, and this is going to be negative sine of the phi, sine of the phi. See, that's going to be the one. If you distribute it, you you can do, if you have done linear algebra, you can do something, you can, for example, pull out the sine of the phi here, but, I just give you I give you eventually the final answer. But if you want to do it, so get this determinant, a little bit of trig functions. Okay, so it's going to be equal to the I times, you see, this would be only, we get the negative. So we get the negative cosine of the data, sine square of the phi. Okay, that's going to be 1. So this is what we get for the first one. Then minus j times, eliminate the first dot. So we get only this, negative positive. So that gives you the sine of the data, sine square of the phi again. Okay. So plus k, you get something over here. You see, eliminate this. So then you get this too. Okay, so we get what? We get negative sine square of the data, then the sine of the phi, the cosine of the phi, the sine of the phi, cosine of the phi. Okay, and then it's going to be minus. It's going to be minus a cosine square of the data. It's a cosine square of the data. Then the same thing, sine of the phi, cosine of the phi, if you can see it. Okay. So what is going to be the leftover over here? So what we can do is going to be, there is going to be a similar, so there is going to be a common factor, if you like. I'm going to pull out the sine of the phi, then the leftover can be easily simplified. Okay, you get negative sine squared, cosine squared. You can factor out this to see if you factor out this part. If you factor out this part, this is going to be 1. The leftover would be 1. So this sine squared, cosine squared would be 1. So the leftover is going to be just k sine of the phi. And this is it. This is it. I just factor out 1 sine of the phi. You could factor it out here as well. So if you factor out the sine of the phi, the leftover is going to be this one. Okay, so the leftover is going to be negative cosine of the data, sine of the phi times I. It's going to be minus j, sine of the data, sine of the phi. Okay, and the last part would be minus k cosine of the phi. You see, that's going to be what? You see, when you're factoring these two terms, you see this all together here. all together here, if you factor out the sine phi, cosine phi, sine square, cosine square of the data would disappear. So this would be minus k sine of the phi, cosine of the phi. Okay, I pull out one of the sine of the phi, so that's why I get cosine phi here. Okay, everybody happy about it? So there is a common factor here, sine phi, cosine phi out, that gives sine square plus cosine square, which is 1. So that would disappear. And for the leftover, I just pull out the sine of the phi. Okay, so this is going to be, so look at this, this one that you got over here. So you have cosine theta sine of the phi, and you get sine theta sine phi, and you get the k cosine of the phi. If you put them together, really what you have is again the just R of theta and phi. So simply just make it a conclusion that you can use it anytime you like. So the normal vector, you see the normal vector for the sphere is going to be sine of the phi. Okay, it's going to be sine of the phi times it by R of the theta and phi. You can get this one as a, okay, as your normal vector, or write it down. You can bring it to the test, and this is it, because it takes times and it's very popular in case of application problem. That would be sine of the theta, sine of the phi, and the cosine of the phi, whichever you are happy about, memorizing this one. So this is going to be the normal vector, okay, to the sphere, to the unit sphere, if you like, unit sphere. Because it's number, it doesn't matter really, even there is going to be a rho involved, because eventually, when you integrate it, that whatever coefficient it is, it's going to be canceling out. Okay, so I just did it so that you know it. So we have a couple of problems in this case. So you better memorize it. Otherwise, okay, it would be okay. Otherwise, it takes times to be able to do it. Okay. So this is going to be doing it. Okay. That is going to be the case. So going back to the formula, remember we were looking for what? We were looking for that integral. So from now on, we know what to do. So we have the n. So go back to the function, and you have to find the f dot n. So your function is going to be what? So the function f is going to be, this is it, x, y, 0. This is your function. Okay. And your r of that, you know that the r. So this is your r. So this is your r of theta and phi, as you have it over there, cosine of the theta, sine of the phi. I just repeat it again, sine of the theta, sine of the phi, and cosine of the phi. So find f of r of theta and phi. Just substitute for x and the y. So that give you cosine of the theta, sine of the phi for the x, sine of the theta, okay, sine of the phi for the y, and the 0. So this is f. Then you have to find the f dot n, which is going to be equal to, remember this is n. You can write it down in whatever format you like. So this is your f, which is going to be cosine of the data, sine of the phi. Okay, and that would be sine of the data, sine of the phi. Okay, and 0. And this is going to be dot what? Dot n, which is sine of the phi. And you just repeat those. Cosine of the data, sine of the phi, sine of the data, sine of the phi, and cosine of the phi. If you multiply them together, everything would be canceled out. If you multiply them together, you have a factor outside. This is going to be the outside. And you multiply these, that give you cosine square of the data, sine square of the phi. Okay, sorry, that's a parenthesis because it's a dot product. And that would be plus sine square of the data, sine square of the phi, and plus 0. Okay, you pull out the sine square of the data as a factor. So this is going to be sine of the phi. You factor out the sine square of the phi. So the leftover is going to be cosine square of the data plus sine square of the data. This is 1. So your function is going to be sine phi, sine cubed. Any question? So at the end, you get something nice, but you have to carry this one with you to the, okay, as your formulas, and be accepted if you say there is no normal vector. Okay, so there you are. We are ready to give you the flex. So the flex is going to be double integral of the f dot n ds. Okay, f dot ds over the surface. So we switch it into the domain f dot n, but it's going to be d data d phi. So what is the domain? Domain is a hemisphere. Since hemisphere, the data would be between 0 and 2 pi. Since it's a half a sphere, so phi would be between 0 and pi half. And the function is just a sine cube of phi. And then we get as I did it, it's going to be d phi d data. Any question? Remember, it's a hemisphere, so the data is free between 0 and 2 pi, but phi would be between 0 and pi half. Sine cube, remember, if you want to integrate the odd power of the sine, you pull out one sine, change everything else to the cosine to integrate it. So this is the way you're going to integrate it. I take this one out and integrate it first. It's a 0 to pi half sine cube of the phi d phi. So I rewrite it 0 to pi half. Rewrite it as sine square of the phi times sine of the phi d of the phi. You keep this one for the u prime and change the sine square into the 1 minus cosine square. So it's going to be 1 minus cosine square of the phi. Okay, times it by the sine of the phi, d of the phi. Now we are ready to integrate. Okay, you can multiply it inside if you like. 0 to pi half. 0 to pi half sine of the phi minus cosine square of the phi times sine of the phi, or d phi. Integral of a sine would be cosine. So that gives you negative cosine of the phi. And over here, integral of the cosine square would be plus sine square of the phi, sine square of the phi over 2 to be evaluated from 0 to pi half. Okay. And it can be done easily. If you put the pi half, the derivative cosine of the pi half is 0. Sine of the pi half is 1, so that gives you 0 plus 1 half. Minus, if you put the 0, the cosine of the 0 is 1, so that gives a negative 1. And it's going to be plus 0. So that gives you 1 half plus 1, which is 3 halves. Okay, but remember, you're not done. You have to come back and integrate from 0 to pi to get the final answer. Okay, I'm just doing over here. So eventually you get the 0 to 2 pi 1/3 of the d data, which is going to be, sorry, I made a mistake here. No, that's a 3. So that was negative 1 plus, did I miss anything? Yes, that's a cosine square. Sorry, this must be sine cubed. Sine cube over 3. Because the cosine squared, you integrate it, would be cosine cube. Cosine cube, so everything is going to be all right. We put the pi half 0, that give you 1/3. That give you 1/3 minus, if you put the pi half, if you put the 0, that give you 0. That would be, that's a 3. The answer should be 2/3. Okay, I have to check it again. I put the pi half. You see, if I put the pi half, that would be 0. So that would be 1/3 minus, if I put the 0, cosine of 0 is 1. So that give me a negative 1. Okay, and then 1/3 plus 1, 4/3. I think that's 4/3. 4/3. I think that's 4/3. Okay, so eventually this is going to be 4/3 times 2 pi. It seems to be the integral is going to be 8 pi third. Okay, you can double check it, but I think that's correct. So that's a flex over the unit. Okay, on the unit sphere. I did it because this evaluation on the unit sphere is very popular in physics. So if you take those courses, you may have to do it and you have to know it. Over there, they just throw it out without any explanation. So that's why I want to make sure that we are ready for it. Okay, but the one that you have are going to be a little bit easier to be able to take care of it. Okay, any question? So this flex in application problems, sometimes, most of the time it's nice, nicely can be done. Nothing to worry about. But there are some helps to be able to take care of these, especially if you're doing something in physics. As I talk about it, the guy who did this type of problem for the first time, of course, is Friedrich Gauss. He introduced this integral, and since these integrations are sometimes, it would be difficult really to handle, what he did, he just extend a version of the Green's theorem, and that make it easier to be able to do this. The version that we are going to do, we are going to extend it. That was at the same time was done by somebody else. Somebody else, of course, is George Stokes. Stokes did the generalization of the Green's theorem. I call it Stokes theorem, that enable us to find these integrals with different tools. But what I'm going to do is I give you the notion of the Gauss first, then we end up with the Stokes. So there are 3 famous theorems in calculus 3, then we are done with all the 3s. Okay, but I'm not going to give you anything from this Gauss format on the test. But if you want to use it, you are okay. you are welcome to use it. But officially, it's not under your review. But I want you to see everything, so that we have it. Because that's part of history of science, really, history of physics, that they do this type of ideas. Okay, so what is that idea of you see, Gauss, you know that Gauss has done quite a lot. He's the guy who created the complex numbers for the first time, and then complex analysis, really. And he's the guy that for the first time proved that, that every equation of n degree would have n solutions, but some of the solutions can be complex numbers. That's due to the Gauss only. Okay, he was a great, mathematician, and he has done since he was, it says, it was 7 years old. He's done quite a lot. But in the course of doing that phenomena that I talk about it in the case of the heat flow, because we talk about the rate of change of the heat flow through a solid, through the object, through the body. It's just this surface integral that you did. If you have a vector field, you evaluate double integral, that gives you the heat flow. And this is why they are popular. So in the course of doing this, he just realized that this flux integral can be found much easier. So his result is called the divergence theorem or divergence theorem. So what is going to be divergence or divergence? See it? So what is? It's quite nice one. I'm not going to question you on this one directly, but you can use it if you like. Be focusing on the Stokes theorem would be too much. So this really is Gauss theorem. Gauss, Gauss. You can have another S or just S. Gauss theorem. But they refer to it as a divergence theorem. So what's a divergence theorem? It's very much like the fundamental theorem of calculus. Remember the way we do the operation really is, what is the fundamental calculus? We did it before. So you find the antiderivative, which is f prime. Remember, integral of the f prime. Antiderivative of the derivative of the function is just a function. So you write it the f of b minus f of a. You just put these together, but in all these integral that we use so far, we use the double integral. But the Gauss theorem used the triple integrals. So the Gauss theorem will tell you that if you want to find this, this fluid flow, if you like, or the fluxes, or the integral on the surface, you can change it to the triple integral if you like. And sometimes it would be very useful, okay? There are some expressions that you can ignore it. So what I'm going to do, like in the Green's theorem, remember in the Green's theorem, you did have a boundary, and then you have a boundary of the domain. Then we show that the integral on the boundary of the domain, which was a line integral, can be done by integrating on the domain. It's a similar thing. So if you see some undefined terms, just think about the sphere and its boundary, if you like. So let E be, we call it a simple solid, like the sphere, solid region, and let S be the boundary of a surface, be the boundary of the surface E. Okay, that's it. So i.e. S is the boundary of E. Expression like the Green's theorem. If it's going to be the case, now let F to be a force, F be a vector field, be a vector field whose component functions have continuous partial derivative, have continuous partial derivatives. Continuous partial derivatives. Okay. Okay, on E if you like. If this is going to be the case, then if you want to find the flux or the rate of the fluid fluid, then the double integral on S, which is the surface, remember it's the boundary of the E, F dot ds is going to be the same as we see this the one, triple integral. Triple integral of a divergence. Remember the divergence? The one that we did before. I told you we are going to use it. That's it. On the solid E. Nice. This is the only theorem that expresses the surface integral in terms of the triple integrals. Otherwise, they are all double integral. That's why it's interesting. Some people, they say, oh, look at this as a derivative, if you like. Look at it as a derivative, and you're just integrating, it's integral of the antiderivative of the function would be the function. It's the way, they justify it. And it's not difficult to prove. You see, that gives you the choice. If the surface integral is complicated, you can change it to the triple integral and just do it right away. Okay, so that gives you an advantage. Okay, I just give you briefly one example just to know it, but we are not going to test you on this. It's very good to know, especially if you are measuring physics or just doing something, electrical engineering, etc. You need it, you have it. So we wanted to see it. So that's it. Example is going to be give one field just to show that when you can use it. Evaluate this integral, the double integral of f, okay, f dot ds over here, ds over s. But look at the force, where force is f the field. So look at the vector field. The vector field is x, y, I plus y squared plus e to the x z squared j plus sine of x, y, k. And what is the surface? And S is the surface, of the region E bounded by the parabolic cylinder, The cylinder is z equal to the 1 minus x squared, and the planes, z equal to the 0, y equal to the 0, and x plus y equal to 2. It's going to be just all planes. So you have this paraboloid one, it's just is bounded by these planes, like a solid piece of chocolate or something. That is going to be a box, something that you see. You have this cylinder in XYZ, you have this cylinder XYZ, and then you have those lots of boxes around, if you do it. You see, if you want to do it with the method that we talk about, it's very complicated. Because if you want to do it with the method of the surface integral, you see your surface. So it would be very difficult to handle this domain or this solid that you have. But if you do it with divergence, it's very easy because you have the restriction for the x, y, z, and quickly you integrate it and you're done. So when it's complicated, So why not? You can use the divergence theorem to do it. Let's look at this one. Remember the divergence of the F? What is the divergence of the F? If you want divergence of the F, remember round F, round X, round F, round Y. Okay, and it's going to be round F. Okay, round F, round Z. I think that was the one that we did have. Or those component vectors, sorry, those component vector. Let's say this is going to be M and P, if you like. You differentiate each components to get to the divergence. So if you do the first one, so I rewrite it. It's going to be round X of the first function, which is X times Y plus round F round Y of the second function, which is Y squared plus E to the X Z squared, and round Z, the third function, which is the sine of XY, is a scalar function. So derivative of this one respect to the X would be Y. This one respect to the Y would be 2Y. And the derivative of the last one would be 0. Say we get 3Y. Nice. So when you want to integrate, you see the divergence is going to be 3Y. So just integrate 3Y in this region that you have. Okay. And the domain, you see, your solid is what? Is a collection of points X, Y, Z. In what? Your X is between -1 and 1. Your Z is between 0 and 1 minus X squared. And your Y is between 2 minus Z. You see, that's a domain. Because the Z is between 0 and 1 minus X squared. Y 0 and 2 minus Z. And the X, if you put Z equal to 0, X would be between -1 and 1. So triple integral of the 3Y over this region. Done. You see, great theorems that you know. You don't want you to miss it. But just set up the the integral and to give you the result, and you can check it for yourself if you like. So this is it. So the flux divergence theorem is equal to the divergence or divergence of F. And what is this now? It's going to be triple integral of the 3y dv over the E, which is, you see x is -1 to 1, y is 0 to 1 minus z squared, and 2 to minus z. Function 3y differentiate respect to the y, respect to the z, respect to the x. It's very easy to find, I just do it for yourself. 184 over 35. So that gives you the great Gauss theorem in order to evaluate this surface integral. Again, since it's so popular and frequent in application problems, so that's why they were looking for different methods to be able to do it. And it's very nice to connect them together. Okay, so we are not going to give you the divergence theorem. I'll give you a break. We come back, and there is another method to do it. That's extension of the Green's theorem. We call it the Stokes theorem. It's very similar to this one. And then we give you one question on that, and then we are done. So we have these three great names of the calculus 3. It's George Green, okay, George Stokes, and then you get a Friedrich Gauss. That give you 3 theorems: Green's theorem, Stokes theorems, and the divergence theorem. Of course, the foundation of all these 3 are going to be just the Green's theorem. Green's theorem for the function of 2 variables, the Stokes theorem and divergence theorem are going to be, the one for the function of 3 variables. Of course, this divergence theorem was also proved by a Russian mathematician, Okay, so sometimes we refer to his name as well. Okay, I'll write it down for you because it's difficult for me to pronounce it. Okay, so there you go. Let's have a break, 15 minutes. We come back, we give it a nice Stokes theorem. We give one question on the Stokes theorem. So one surface integral from Stokes. Okay, then we are done. So 15 minutes and I'll do it for you. Okay. So what we are going to do, as I talk about it, this is going to be our last theorem. We were working on, it's the one that we did. We were working on the surface integral on the vector field, or finding the flux of the vector fields. So I talk about it, the general formula, we know it, but sometimes it can be connected to the other part of the course. So the divergence theorem was one case. The other thing that we would like to do is we would like to connect this one to the generalization of the Green's theorem. You see, Green's theorem can be used for the vector field in two-dimensional. Remember the double integral, it's going to be the line integral. The line integral would be a double integral of that round Q, round P that we did before, okay? And so what we're going to do, we are going to connect this format into something similar. So let me just remind you what we did for the Green's theorem, and now we do the Stokes theorem. Okay, so this is briefly 15.8, if you like, the last topics that we have, and that's a great Stokes theorem. Okay, they're all connected to each other. Stokes theorem, as I told you, these three famous theorem, the Green, Stokes, and the Divergence theorem. We're working now together to get these results. And now, what we did before, we, when we talk about the line integral, then we just connected to the Green's theorem. Okay, to just remind you about the Green's theorem, then we extend it into the function of three variables. So there you are, recall that. I want you to compare them together. Okay, recall that if, and that's it. Recall that by, I just summarize it, by Green's theorem. Green's theorem is the one that we did. If you want to find the line integral of the function of the form of the p dx plus q dy, remember, if you want to find this integral on the curve C, which is going to be the boundary of the domain D, it would be the same as the double integral on the domain D of this quantity, round Q. Okay, round X minus round P, round Y. That is the case. Okay, this is the line integral. You want to find it. So what we did have a domain here. You see, we have a domain here, and this is going to be the domain. So this domain is bounded, if you like. The boundary of this domain is going to be a curve. So if you want to find the line integral on the curve C, you change it to the double integral into the double integral for these expressions. Now remember, if the force happen to be conservative, these two are going to be equal to each other, and this is going to be zero. So this is going to be used for the closed curve, and the force is not going to be conservative. And as we did this one before for you, I give you the vector form of the vector form. Remember, I changed it a little bit. I call it a vector form of Green's theorem. Okay, we did a little bit of algebra, and we got this vector form that if you have a field f dot dr, of course the field was in two-dimensional, and on the closed curve C, this integral would be the same as the double integral on the domain D, but the curl of f, since it's a vector dot dot a unit vector k dA. You see, we did a little bit of algebra to just change it into this in this form. That the line integral for the vector field, the line integral vector field, it can be expressed into the in the case of the double integral. So in the Stokes theorem, what we are going to do is we are going to change this function from a vector field in plane into the vector field in a space. So if it's going to be vector field in a space, it's going to be p dx, q dy, and one more. Okay, pqr, for example. That gives p dx, q dy. Now, instead of this expression that you see over here, so we use this format because the curve in three-dimensional does make sense. So that would be the curve in three-dimensional that instead of this k, as usual, you need a normal vector, remember? You need a normal vector. So what we're going to do is change this one to the normal vector. Normal vector of what? Normal vector to the, okay, normal vector to this domain. What's going to be this domain? This domain coming from a surface. So instead of the line integral, of course, instead of the line integral, you replace this integral into the flux integral, which is going to be, you get a double integral over the surface S. Okay, double integral surface S, everything would be the same, except it's going to be curve f dot, okay, dot n, if you like. So that gives you another method in order to find the, okay, another method to find this integral, which is the flux, which is the rate of change, okay, of the heat flow, fluid, okay, fluid flow. And that would be, again, useful tool for application in physics. Okay, so just to make sure that what's the origin of the argument. So the origin of the argument is, what is the three-dimensional version of the Green's theorem? Okay, Green's theorem. So that's going to, I just repeat this one, but I have to switch the integrals from the line integral into the surface integral. So we can use the Green's theorem to evaluate the line integral. We can use the Stokes theorem in order to evaluate surface integral. Okay, so that's the idea. Now we can write it down. This is going to be the Stokes theorem. George Stokes, that's it. Theorem. As you can see, his theorem is very much close to the version of the, okay, the work of the Gauss. But, you know, they just do it from a different point of view. Okay, there you are. So instead of a curve, I should start with the surface. So let S be a surface. Make sure you know the difference and when are you going to use it. Let S be a surface with, I need a vector, unit vector, a unit normal, because it's a surface integral. So you need this unit vector n. Now bounded, this curve is going to be, surface would be bounded by a domain, bounded by a smooth, okay, smooth, simple closed curve. Okay, simple closed curve. And that's it, simple closed curve, SC. Okay, C with the positive orientation. Positive orientation is the one that we use for all of them. Remember the direction of the integral. Now, if we've given a force, if F is going to be, is going to be a vector, okay, a vector field. It's going to be a vector field whose component, as usual, as partial derivatives, whose component functions have continuous partial derivatives, have continuous partial continuous partial derivatives on a set, we say open. A statement is like the statement of the divergence theorem on an open region containing, containing S and C. Then you just write this one right away. Okay, but in a set of the D, we work with the surface integral. So it's going to be integral of f dot dr, or C is closed. So this part is going to be different, the surface integral. It's going to be a surface integral. That's a surface integral of curl of f. Okay, curl of f dot n. Okay, dot n dot then ds. ds. There are different way to write this one that I'm going to explain it. Okay, so exactly you just extend this version of the Green's theorem. So over here you have the surface integral. This is the line integral from the past. so we can use it in either format. Okay, from the line integral to the surface integral or otherwise. But this version of the Green's, so the function, you know that if you put them together in differential form, if your function would have so let me just give you the other version. So if you like, note that the integral in this case f dot dr over the C in differential form would be p dx plus q dy plus r dz. Okay, and so this is the version which is going to be kind of extension of the Green's. Integral of a p dx plus q dy plus r dz is going to be equal to the surface integral. Okay, surface integral of the curl of the f. Okay, curl of the f dot n ds. Okay, and sometimes they drop the n and they write it down right away, so we know what we are talking about. Okay, so that gives you different different possibilities, or to be able to find your okay, especially in this form for the surface integral is easier to memorize it to get the curl f, and you know if it's going to be the line integral over here. Okay, so what we would like to do really is to question this one for you. We give you one function, one domain, everything. We ask you to verify it. Verify it means what? Means you are going to find this part using the line integral. You have the parametric equation of the curve, you substitute everything would be replaced to the, okay, the function of the t dt, you find it. Then you go to the other side. The other side is a surface integral. So you find this surface integral and you show that both of them are going to be the same. Okay, so in the ordinary part, one of them would be given to you, find it, but we would like to verify it. So verify means find the quantity of both sides and show that they are equal to each other. You have one of them on the final. Okay, so make sure to do it. The part to the left, line integral, the part to the right. This is quick. And this would take times. Depends on the nature of the function. So you find it on the test and show us both of them are going to be the same. Okay, this is what we call a verification. As you can see now, if your function is going to function, if your force is going to be force on the plane, this part would be 0. So, and the curve would be changing to the rho q over, okay, rho x minus rho p rho y, you get the Green's theorem. So the Stokes theorem is the kind of extension of the Green's theorem. Okay, I should give you 2 examples. One of them is that the surface would be given to you by okay, it's kind of classic one. It's going to be a surface of the equation like z equal to the gxy. And the other one is that the surface would be given to you by a parametric equation. Okay, the second one takes a little bit more time. So be prepared for both of them. Either one would be given to, but the first one is more popular. Okay, so this is your job. It takes a little bit time, but it can be done. Okay, it can be done nicely. And that's a great theorem, really. So as you can see, you connect whatever you study in this chapter together really in one theorem. That's why make it so interesting. Okay, there you are. This is the statement of this theorem that we're going to do. We prefer this type of question on the Stokes for the test. Verify a Stokes theorem. Okay, that's it. Verify a Stokes theorem by evaluating. HS. Explain it, evaluating the surface integral. Okay, the surface integral and the equivalent line integral. Line integral, which means integral of f dot dr over the c. That's a line integral. Can be done by direct substitution. Equal to the surface integral. Surface integral of what? Curl of f. That's a curl of f dot the normal vector ds. For this function, for this field, for the field is f of x, y, z equal to negative y plus z, I plus x minus c, j plus x minus yk. Where is the surface? Where the surface is z equal to. When it's z equal to, that's easier. X squared minus y squared, and the z is positive. You know that the cross section is going to be a circle centered at 0 with the radius of 3, and by itself is just a paraboloid, if you like. Okay, so when the surface is given to this is g equal to the x, z equal to g of x and y, that's easier to find the normal vector. If it's going to be a parametric, it's like the sphere that we did. It takes a little bit of time, and you may have to use that normal vector that I gave you. Okay, and that's it. Any question? Everybody understand the verification means? Find the term to the left, the term to the right. To the left, line integral, to the right, the surface integral. Show that the numbers are the same. That's your job. Okay, solution. Line integral is easier. You can do either one, you know. You can use the line integral if you like first. So we do the line integral first. F dot dr. That gives an idea of what is the solution. So when you find the second one, if you made a mistake, quickly you find out. Okay. So for the line integral, you know the formula is going to be what? So integral of f dot dr over c is going to be integral of what is going to be the one is going to be f of r of t. Remember f of r of t, and that would be dot. Okay, is going to be just a dot r prime of t. In this case, is a px dx. You know this one. That r prime of t, if you like, then d of t. This is it on the domain that you have to identify what is going to be your domain. Okay, on the domain D. So the function is easier because the function is given to in the form of, you see, this is going to be the p, and this is going to be okay, PQ, that's formula PQR. So we can use in this form, which is much easier. Okay, so the easiest form is you have to find a PDX. Okay, PDX, QDY, and the RDZ. So it's easier to operate in this form. So your domain is, this is going to be the surface that you have. You let z equal to 0 to drop it down to get your domain. Okay, so the domain is going to be collection of points x and the y. You get x squared plus y squared, okay, less than equal to the 9. So that's going to be your domain. It's just going to be the point inside the circle. Can be easily, you can easily find the parametric equation of the domain, and then you'll be fine. Okay, so the parametric equation of the domain is r of t equal to the, remember it's a circle, so this is kind of a polar coordinate if you like. So that give you what? R is 3, so that give you 3 cosine of the t and the 3 sine of the t. Okay, and the t is going to be between 0 and 2 pi. So I'm going to evaluate this integral with this information that I have. Okay, so you can use either this one or just easier to use this part. Okay, to put them together. So going to the next page, I have the PQs R, I substitute directly, and then I get the result right away. So this is it. So I start with the integral of f dot dr over c. So I change it into the integral of, so that was the p dx plus q dy plus okay, r dz over the c, substitute. So we change it into the polar form, so it's going to be 0 to 2 pi. I mean, the substitution. Your p is negative y plus z, so dx plus, substitute for q, q is x minus z dy, and then we get z, x minus y dz for the r. Okay, pqr from the function that we have. Now you have to substitute to get the result. Remember your r of t is what? Your r of t is, you have 3 cosine of the t, you have 3 sine of the t. Since you need the third one, is just 0. So substitute. So this is going to be x, and this x is equal to the 3 cosine of the t. So your dx would be negative 3 sine of the t. Okay, your y is 3 sine of the t. So the dy would be 3 cosine of the t. Sorry, dt, cosine of the t dt, and the z is 0. And the dz would be 0. Okay, substitute here and integrate. So integral of the f dot dr over c is going to be equal to the 0 to 2 pi. Substitute negative y. Y is 3 sine, negative 3 sine of the t. Z is 0 plus 0. Dx is negative 3 sine of the t dt. Okay, I'm just substituting. Next one, plus x. X is 3 cosine. 3 cosine of the t, that's x, minus z. Z is 0 times the dy, which is 3 cosine of the t dt. Okay, plus x minus y. So we get 3 cosine of the t minus 3 sine of the t times the dz. Dz is 0. So this part would be disappear. I just substituting. So continue, it's going to be 0 to 2 pi. 0 to 2 pi, we get negative 3 times, and that gives you 9 sine squared, 9 sine squared of the t. Okay, for this one. And over here, we get plus 9 cosine squared of the t, and the last one was 0, dt. Okay, so if you factor out the 9, so that gives you sine square, cosine square is 1. So it's going to be 0 to 2 pi, 9 times sine square of the t plus cosine square of the t dt. This is 1. So you integral from 0 to 2 pi, 9 dt is going to be 9t from 0 to 2 pi. So that gives you 18 pi. Okay, so you know that the integral of the f dot dr over c is equal to the 18 pi. That gives you the line integral. Okay, I find this one first, so I know that I should get 18 pi from the surface integral. Okay, so now I'm going to use find the surface integral. Are you ready? So that was the term to the left. So how about surface integral? Surface integral. Surface integral is the other part. So we have to find the double integral over S of curl of f dot n ds. So that would take more time. You have to find a normal vector. That's your challenge. So equation of a surface. Okay, this is it. A surface equation is of the form of the z equal to the g of xy. G of xy, you see the z was given to you, is equal to the 9 minus x squared minus y squared. We give you the formula for this. You can do it if you like, it's not a big deal. But the g sub x is going to be equal to, g sub x is equal to the negative 2x. Okay, the g sub y is equal to the negative 2y. Okay, negative 2y, and you know that the normal vector for this one, and we already talked about it, is a negative g sub x, negative g sub y, and 1. Make sure you remember this one. That takes you, save you some times. When the surface integral is a function of x and the y, this is the normal vector all the time. Okay, this is your normal vector. So just substitute. So your normal vector now is going to be, that's it. And this is, that give you 2x. Okay, that give you 2x, 2y, and 1. So this is the normal vector. Okay. Now you have to find the curl of the f, then multiply by the normal vector, and then integrate it. Okay, what's the curl of the f? The curl of the f function, remember it's going to be, this is it, the curl. The cross product of the differentiation operator times around delta f, or the gradient. So this is going to be equal to the formula. The first part is going to be I, J, K. The first one is just a differentiation around x, around y, and around z. That's the case. Okay, now this is going to be the function that we have. So the function are going to be what? And this is going to be, sorry, this is just, that's going to be what? Curl is just del cross f. Del cross f, as I put the f here, so the PQR, so that's going to be negative y plus z. Okay, and that was x minus z, and this is x minus y. So get the curl, it's going to be I times cross multiply. That give you round x, okay, the partial derivative with respect to the y, so that give you -1 minus, that give you partial derivative with respect to the z, okay, derivative with respect to the v, which is a -1, so minus -1. That's the first one. Then minus j times partial derivative with respect to the x1 minus partial derivative with respect to the z is 1. Sorry. Plus k times partial derivative with respect to the x1 minus the partial with respect to the y would be -1. 1 minus -1. Okay, so that would be 0. And this would be 0. And this would be 2. So the curl of the f would be 2 times k. So that would be your curl. Okay, 2 times k, or you know that, or curl of f simply is going to be 0, 0, 2. That's a curl of f. I'm working on inside this integral. So I have to get it the dot product with the n. Okay, so I'm going to find the curl of f dot n. So that's the 0, 0, 2 dot n. N was 2x, 2y, 1. So if you multiply them together for that give you 0, 0, it would be 2 only. 2. Okay. So easy function to integrate. Okay, now I'm ready to get the surface integral. This is it, the surface integral. And I had the curl of the f dot n dot ds. So that give me 2 dss. Sorry, the surface integral. Okay. So we change it to the, okay. So we have to do it on the, this is going to be the case. So it's on the domain, remember the domain was a unit circle. So this is going to be equal to the evaluated. The evaluation is going to be the double integral. Okay, the double integral on the domain of the d, and this is going to be 2dA. You know, you just change it to the, simply into the double integral. But remember, your domain was the unit circle, and we already take care of this one. Okay, it's less than equal to, it was less than equal to the 9. Less than equal to the 9. So we change it to the polar coordinates. The polar coordinate is that r is going to be between 0 and 3, and the data is going to be between 0 and 2 pi. So change this integral into the, okay, change this integral to the double integral in polar form. So it's going to be 0 to 2 pi, and the r is 0 to 3. It's a 2, but extra r, then the dr, d data. Any question? Then you integrate respect to the r, that give r squared. So it's equal to 0 to 2 pi, and that would be r squared, r going from 0 to 3, then the d data. 3 squared would be 9, so it's going to be 0 to 2 pi, 9 d data. And you know that integral of 9 would be 9 data. 9 times 2 pi would be 18 pi. Okay, so this is going to be equal to the 18 pi. And we did it. You know that the other part was also 18 pi. So the double, the surface integral. The surface integral is also 18 pi, and the formula is verified. Okay, so that the purpose of this problem is you just, you just do everything we talk about it to get this one through. So again, it's not difficult. It takes a little bit time to do it. The one that you have on the test is not bad. It can be done quickly, and you have another one on the practice one that I do it tomorrow for you. But I should give you one more. Okay, and this is where we try to give you of this type, but you should be aware of, because the surface over here was equation of a surface was directly given to you. It was an explicit surface, z equal to g of x and y. The challenging one, if this is not going to be explicit given, so we have some quadratic, those form, like the sphere. Okay, the one that I did over here was paraboloid, so it was not z squared. When it's going to be z squared, it takes a little bit more time. So you may need the normal vector to the sphere, and that's the purpose of this problem. Okay, so I'll give you one more. This is going to be the last one that we're going to have. But one of them, we try to give you a shorter one on the test, but we want to make sure you know how to handle it. Okay, so let's verify that for this function. Again, this case is very popular. Let me just bring it. And you have two on your practice one. All you have on your practice one are of the type 1. That's why I should give you this one. Okay, so this is our last example. We want to verify this time for this one. Verify Stokes. So you have many choices. You may not use the Stokes theorem most of the time, okay, but from the theory point of view, when you do in application problems, so you are going to have it for some other purposes, and for this type that you see in applications. Okay, verify the Stokes theorem for this. The Stokes theorem for, and the force is this one, vector field. This function, it's a negative y, 2x, and the x plus z. That's a vector field. And again, this is it. And the surface is that upper hemisphere. So, and the upper hemisphere, with usual, they say outward pointed normal vector, so that the condition satisfy normal vector. And the S is this one. Okay, this is a normal vector onto normal vector out of or onto the surface. It's a sphere. Okay, this is it. Let's say with the equation. This is the surface. Okay, it's a sphere, hemisphere. So you have a collection of points x, y, z. So they satisfy x squared plus y squared plus z squared equal to 1. Okay, and of course z is positive. So it's going to be upper hemisphere. Okay, that's it. This is where you need that normal vector and the one that I gave you already, so we can use it. So the difference is this. In all the other problems, if you can solve for z, that's easier. You see, you just go with the g sub x, g sub y that I gave you, and we are going to repeat it, give you, go over it tomorrow and show you. Okay, so there you are. So what do you want to verify? We want to verify that the f dot dr, okay, the line integral over the c, which is going to be a boundary of the sphere, okay, is equal to the surface integral on the sphere. Surface integral of the curl of the f dot n ds. Okay, this is the one that you want to show us. Again, you have two cases. You can start with either one, okay, to get this done. Again, my suggestion is go with the line integral first, until you get the number, so then you know what you are looking for. Okay, so solution is going to be, we go with the line integral again. Okay, so take the line integral first. So the line integral, you have to find this one, f dot dr over c. Okay, you know, you can directly substitute because the f is given to in vector form. And so get the equation of your c. C is going to be just the, okay, it's going to be boundary of the sphere. Boundary of the sphere is going to be just a circle. Okay, so your c is the boundary of the sphere, unit sphere. So the c is going to be the collection of x and y on and inside a unit circle. So this is your case. So the radius is 1. So your r of t, as usual, is going to be kind of polar coordinate. It's going to be cosine of the t. R is 1. Remember that. Cosine of t, sine of t. And the two-dimensional, but you put the 0 for the other one because your force is in R3. Then you have to find the R prime. Okay, this is it. You find the R prime of t. So the R prime of t is a negative sine t, cosine t, and 0. That's R prime of t. Then you have to find the f of rt. So f of r of t is going to be like f of cosine of t for x, sine of t for y, and 0. If you substitute in your function, so you're going to end up with, remember the function was, this is your function, negative y2xx plus z, substitute for the x, y, z. Okay, x cosine, y sine, and the z 0. So the first component was negative y, and negative y, so that give you negative sine t. That's the first component. Okay, the second component is 2x. So 2x would be 2 cosine t. And the last part is x plus z. X is cosine of the t and the z is 0. So that gives you cosine of t plus 0. Okay, so this is going to be your vector. Then you have to get the dot product of these two and integrate it. So you find f of r of t dot r prime of t. Okay, so this is it. So this is r prime of t, just multiply these components together. So that gives you negative sine t times negative sine t plus the component. The second component is cosine t, 2 cosine t. And the third component, of course, is 0. So that gives you 0. Okay, the result must be a number. So this is going to be sine squared of t plus 2 cosine squared of t. Remember, you want to integrate, so you better simplify it. So this is 2 cosine squared, right? On cosine squared plus cosine squared. So that give you, 1 plus, so this is going to be like a sine square of the t plus cosine square of the t, then cosine square of the t. So this would be 1. So that'll make it to the 1 plus cosine square of the t. Okay, so make it something nice and then you integrate it. and then you'll be done. Any question? So this is it. So the line integral f dot dr over c. So it's going to be equal to, so this is the result. It's going to be 1 plus cosine square of the t circle, unit circle, no restriction 0 to 2 pi, and then the dt. You have to integrate this one. You know that you have to change the cosine square into double angle to be able to integrate it. So it's going to be 0 to 2 pi. Okay, and that's going to be 1. Cosine squared would be 1 plus cosine of the 2t divided by 2. Okay. Then you can integrate it. It's going to be 1/2, and 1 would be, okay, it's going to be 0 to 2 pi. Okay, 1/2 and 1/2 would be 3/2. That's going to be 3/2 times cosine of the 2t over 2 dt. Now integrate it. So that gives you 3/2 of t. Integral of a cosine is just sine, so it's going to be plus sine of the 2t divided by 2. You already got the 2 cos 4, so that would be 0 to 2 pi. Sine of the 2 pi and the 0, both of them are 0, so you won't get anything from the second part. The only thing that you get from the first part, so 3/2 times 2 pi. Okay, so this is going to be 3/2 times 2 pi. So the result would be 3 pi. Okay, so the line integral f dot dr or c would be 3 pi. So that gives you the idea that you're going to have it for the second one. So that's a line integral. Then you have to take care of the surface integral and show that you get the 3 pi again. Okay, any question? So do the line integral first, so that at least you have the answer for the second part. Now, and the challenge for this one is for the surface integral, you need the normal vector. And since this is the sphere, you must know that normal vector in advance, the one that we did. Otherwise, it takes quite a while to find it. That's why I give you this one. I know I gave you the formula. Okay, are you ready? So going to the second part and taking care of the surface integral. Okay, surface integral. So for the surface integral, you have to find the double integral over the surface, and that's a curl of the f dot n ds. This is what you have to do. You have to have the parametric equation of the surface. It's of course a sphere. So we use remember this is it. S is just x squared plus y squared plus z squared equal to the 1. So that gives you rho equal to 1. And the parametric equation is going to be a spherical coordinates. Okay, so we get the parametric. So the spherical coordinates for rho equal to 1 is going to be the parameterization is the parametric equation of S. Okay, so there you are. R of the data and phi is equal to rho is 1. So that's the cosine of the data. Remember sine of the phi. This is sine of the data, sine of the phi. And the last one is cosine of the phi. Remember rho is 1. And we already talked about it, so you can use it. And that's it. Note that the normal vector in the case of the sphere is, okay, this is it. Your normal vector, I gave you this one. It's the sine of the phi. Sine of the phi times z times r of the data and phi. The one that I proved. So anytime you need it, you can use it. Otherwise, it takes all your time to find it. Okay, so this is going to be your normal vector. You know, you can multiply by r of theta, which is over here, to get your function, or just keep it as is. And then, okay, so this is it. So find the f dot, okay. So what we need for the next step is going to, we need the curl of the f, then dot n. So bring the f and find the curl of the f. So what is your f? So this is f. So f is what? F is x, y, z, which is going to be negative y 2x and x plus z. Okay, this is going to be the case. So you can find the curl of the f, then evaluate it at okay, evaluate at the x, y, z that you have on your function. Okay, just to put them together. So let's do it. This is it. So we get a curl of the f. Okay, the curl of the f, then dot n to be able to do it. Okay, this is it. So the curl of the f, you know, that's going to be I, j, k, and that's going to be round x. Okay, round y, and the round z, the function. It's a negative y. This is a 2x, and that would be x plus z. Okay, so it's going to be equal to the I times. So eliminate this, respect to the y, that give you 0, minus respect to the z, that would be 0, nothing here. Okay, plus j times j, respect to the x is 1, minus respect to the z is nothing, so plus k, respect to the x2, respect to the y negative 1. Okay, that's it. So we got the 0 here, and we got the 1, and we got the 3. So the curl of f, the curl of f is going to be j. Okay, it's going to be j plus 3k. It's all constant, which is very good. So in vector form, it's going to be 0, 1, and 3. If it's going to be anything else, you have to substitute x and the y, z from that curve that we have, but you don't need anything because it's just a constant. Okay, now you have to multiply by the n and then do the job. Okay, that's a curve, and this is the n, which is the sine of the phi, and this is r of the data and the phi. So if you do the dot product, so the curl of the f dot, okay, dot n is going to be equal to, you can keep this sine of the phi as a factor, and then you get the dot product of this, which is going to be 0, 1, 3 dot that polar coordinate that we have. Remember, that's a cosine of the data, sine of the phi, sine of the data, sine of the phi, and then you have a cosine of the phi. If you multiply it through, so that gives you sine of the phi already, and the rest are numbered. This gives you 0 plus 1 times sine of the data, sine of the data, sine of the phi, and 3 plus 3 cosine of the phi. So if you multiply through this, give you nothing. So this is going to be equal to the sine of the data, sine square of the phi, plus 3 sine of the phi, cosine of the phi. You see, that is the quantity that you have to differentiate. Sorry, you have to integrate. Any question? So we want to integrate it. You know that it's going to be a hemisphere. So in that case, you have the data and the phi that we get over here. Okay. So your data is going to be between 0 and 2 pi. And your phi is going to be between 0 and pi half, because it is just a hemisphere. Okay. So we are going to go to the next page and integrate this one in this domain and show that this is going to be the case. Okay, so I'm just going to back and substitute and integrate it. Just make sure I get everything that I need. Yeah. And I hope to get the 3 pi. So this is it. So the double integral of the curl of the f dot n ds on that surface is going to be equal to the integral from 0 to pi half for the phi, 0 to pi. Okay. Why is the pi? It's going to be 2 pi. Okay. It's going to be 0 to pi half, 0 to 2 pi, and this quantity that I simplified, it's a sine of the data. Okay, sine square of the phi, sine of the data, sine square of the phi plus 3 cosine of the data, cosine of the data, and that is sine of the phi. Sine of the phi. So I'm going to integrate it respect to the data first and then the phi. Okay, I simplify everything. I change it to the in terms of the phi and the data. So carefully integrate it. So you break it in 2 parts and it can be integrated somehow easily. So I integrate respect to the data first. So it's equal to the 0 to pi half. Integral of a sine is a negative cosine. So that gives negative cosine of data, the sine square of the phi. Okay, integral of a cosine is just sine. And that gives me the sine of the phi. And this is going to be evaluated when data is going from 0 to 2 pi. And then I get the t of the phi. Okay, a subset for data. So if you put the 2 pi over here, that gives you a 1. Okay, so it's going to be 0 to pi half. I put the 2 pi first. You see the cosine of the 2 pi is going to be 1. So that gives me negative sine square of the phi. If I put the 2 pi over here, the sine of the 2 pi is 0. So that gives me 0. Minus, if I put the 0, cosine of the 0 is 1. So that gives me negative. Okay, negative sine square of the phi. Okay, and if I put the data equal to the 0, then the sine of the 0 is 0. So that would won't give me anything here again. Okay, and there is a 3 here, sorry. That's a 3. Okay, that would be 0. That's it. So 0 to pi half. So negative would be positive. So that give me negative sine a square of the phi. Okay, plus 3 sine a square of the phi. D of phi. So that would be 0 to pi half. And that give you 2 sine a square of the phi. Okay, 2 sine a square of the phi and the d phi. You know, you put it out, it's a double angle formula. So replace sine square by 1 minus cosine. 1 minus cosine of the double angle and the d of the phi. So 2 and 2 would cancel out. I integrate the leftover 0 to pi half 1 minus cosine of the 2 phi and d phi. Okay. Now, if you integrate it, so that should give you the phi. Okay, that give you the phi, and this is going to be what? This is going to be minus the sine of the 2 phi over 2 from 0 to pi half. Okay, 0 to pi half. And if you substitute, so that give you pi half, that give you 0. If you put the 0, that give you also 0. So I should have missed something that I didn't get it over here because I need what was the answer? 3 pi. So that's a pi half. That give me the pi half minus the sine of the pi is 0, and that would be 0 too. Probably I miss a coefficient, something. Okay, any suggestion? I haven't done it before, so I don't know whether you had the cosine of the data instead of cosine of the pi. Which one? Where do I have cosine of the? You see the one that I did over here. This one is the one you mean? 3 cosine of the. I think this one. You are right. Yes. Yes, excellent. Yeah, this must be phi. Yes, you are right. So this must be phi. Okay, so this is 3 cosine of the phi and then sine of the phi. Yes. Let's see if we can correct it. So when we integrate here, so that was the one. So when we integrate, this would be unchanged. Okay, so this would be unchanged. So when we substitute, so that's a cosine of the phi. So that is cosine of the phi, sine of the phi. Yes, that's a cosine of the phi. That's cosine of the phi. So when we substitute, this part is all right. Okay, so that gives us when we substitute, cosine of the data, of course, is going to be 0. Yes, there is no data here. So in the second part, okay, when we substitute here, that would be fine. In the second part, when we put the 0, cosine of 0 is 0, and here, then when we put the data equal to the equal to the 0, so this would be unchanged. Okay, so this would be unchanged. So this would be 3 cosine of the data, sine of the phi again. Yeah, I missed this one. You have to do correct that. I can rewrite it then. Then when I post it for you, I just rewrite it, because I know that, it must be 3 pi, of course, because this is going to be the case. So I rewrite this one. I give you the correct version. That's correct. Yeah. Yeah, because we have this, when we substitute the 2 pi, we are fine for the data. So that give us, so this would give us this is correct. Okay, we put the 2 pi here, we repeat this one, and then we put this would disappear. This would disappear, so you are going to have only sine square of the phi here. The sine square of the phi, and you don't have this quantity here. But when I post it, I just do it for you, because this would disappear, so you stay with the sine square of the phi. So this would be 1 minus cosine of the data over 2. So these two would be unchanged. Okay, and so we just we break it down. And that gives us 1/2. Okay, that gives 1/2. That would be a core there. Then we should be able to. But I rewrite it for you. Okay, when I post it, I will eliminate this one. Then I put the correct one. When I scan it, then I can eliminate that part. But it would be 3 pi. I guarantee that. Okay, so this is 2 different versions of the Stokes theorem. Mainly, they give it type 1 because it takes time, but you have to know this type of ideas, to be able to get through it. Okay, that's it. So what I'm going to do, I will grade your quiz tonight. So that's how you did it. So tomorrow, there are something like 4 or 5 of those problems on the review that we have to do it again. You read it yourself. But there are a couple of integrals that I have to explain it for you. And I give you the problems on the on the Stokes theorem. So we go over those numbers. Otherwise, we are done. Okay. Any question? So do the quiz, study the final review. All the problems are already there. But tomorrow I give you some kind of, I think it's a problem like 25, 26, a couple of them. Use substitution, then there are a couple of points that we have to explain. So I explain those, and we are ready for the final. Okay, 13 question on the final. Okay, I'll be 5 to 6. I'm available. You email me first if you want to come to Zoom. Then I'll be I join you, and then you can ask any question. Yes, I'll be on the available, but you email me first. Okay, so just as I told you, focus on the quiz and the 2 questions from today, 6 and 2, okay, 8. And a couple of you missed some points on that something like double integral, that exponential function, question number 1. Some of you missed it, so check the solution that I posted for you to be able to. Otherwise, you'll be fine. Nothing to worry about. Okay, have a good one, and see you tomorrow for 6 problems from the final review that I have to explain. Okay, have a good one. Bye-bye.